Good morning again. And this is the track Q31. No, is it Q31? Yes, it's Q31, Post-Quantum Crypto Timing and Standards. And my name is Nithya. I will be the moderator for this track until lunchtime. And we have our first speaker from Switzerland. And that's Basil Hess, and he's a senior research engineer from with IBM Research, and he will be talking to us about tooling for detecting timing leaks, not just in quantum safe implementations, but other implementations as well. Please give Basil a hand and welcome him.
Thank you for the introduction. So my talk is about timing leaks in cryptographic implementations, so specifically in quantum safe ones. And then we'll talk about some tooling that you can use where you can verify if your implementations are actually constant time or if they have timing leaks. So about timing leaks, side channels are very essential in cryptographic implementations and for their security. And let's say while the correctness of implementations can be assessed or is assessed very frequently, right? You have test vectors, you have test programs for your implementation, so you can make sure that it's correct and it interoperates with other implementations. But testing for side channels is usually very difficult, right? And many things can go wrong there. There are many different types of attacks, like the channels are timing, right? You can measure things like EM emissions, power consumption. You have invasive attacks, non-invasive attacks, right? If you have access to the hardware, you can directly probe on it, or you can make some remote attacks. There are fault attacks where you want to kind of change the behavior of the program by flipping some bits or so. You can measure single traces or multiple traces with differential analysis. So, this talk is mainly about software libraries and what you can do there, right? So, usually at least non-invasive timing attacks are kind of in the threat model of software libraries. But we have seen, for example, throughout the standardization process of NIST, there were many reference implementations submitted, and over time there were several examples of timing leaks that were discovered. So it's really the goal to have some tooling in place that can be used to detect that early on and not just, let's say, in the process. So I will talk about mainly three types of timing leaks. The first one is like the definition, secret-dependent control flow, right? What is secret-dependent control flow? So if your control flow, if you have conditional branches that depend on secret data, or if you have table lookups where the index is a secret value, that's secret-dependent control flow. They are, let's say, classical examples for that. If you do a textbook implementation of RSA, square and multiply, modular exponentiation, right? Naive implementation, you will do a square or a square and multiply depending on your secret, and similarly in elliptic curve implementations. And AES, right? If you implement it just straightforward, you have a table-based implementation that leaks secret data. So what's a situation, for example, in post-quantum implementations? There is one kind of central building block in many key encapsulation mechanisms that were now standardized, like MLChem is one of them. It's a so-called Fujisaki-Okamoto transform, where the goal is to have something called CCA security, which is sometimes also mentioned like resistance against active attacks. So there, basically, the adversary has access to a decryption oracle and can change the ciphertexts and gets the plain text of it. And FO is a construction to convert a CPA secure scheme to a CCA secure scheme. And in a nutshell, it works like that. You have the ciphertext, you decrypt it. Under the private key, you get a plain text. And rather than returning it right away, you re-encrypt the plain text with the public key and get the ciphertext again, and you compare the ciphertext that you got with the original one. And if they match, you can output the plain text, and otherwise you get some random message. So, I mean, this has to be side channel protected. And one thing that was also termed the FOcalypse is this equality, right? Needs to be protected. Now, if you look at some implementations, there was, for example, the reference implementation of one submission to the NIST PQC, Fro.chem, but the same code was also used in some other implementations, where what you see there is basically this is the final check for equality, and was implemented with memcomp, right? And now, if you don't know how memcomp is implemented, you think, okay, it's constant time implementation. That's wrong, right? Because it's usually in the C library, it's not a constant time implementation. So that was an issue that was discovered throughout the process. And so the question is, how can you detect something like that? If you write, I mean, everyone can make mistakes, right? Especially if you write C code, how can you detect that then later on? So one very handy tool for this is Valgrind. Valgrind is actually a dynamic analysis tool to detect memory errors. But I think it was the original idea of Adam Langley in 2010 to use this to detect secret-dependent control flow. So the idea there is, or the observation is, usually the output of a random number generator. That's secret data. And if you have any jumps or table lookups depending on that secret data, that's what you want to detect. And with Valgrind, you can actually mark, or what you can do is you mark just output of RNG as uninitialized data, and then you will detect such things. There are some limitations about that. I mean, false positives. For example, some like MLChem and MLDSA, they use something called rejection sampling to get some distribution, which is basically a loop. And Valgrind would flag that as which would be a false positive. Also, if you happen to have a memcomp implementation that is constant time, you will not detect it. Also, if you run it on a different system, then it would be. And yeah, so the platform support is also a bit limited. For example, if you have AVX 512 or RISC-V, that's not supported there. There is an alternative, this the LLVM memory sanitizer that can be used in a similar way. So if you want to test this particular code, here what you see is, okay, Valgrind actually noticed that there is a conditional jump in the bcomp function, which is actually the implementation of memcomp. So this can be detected. So one example of a crypto library that uses this tooling is Open Quantum Safe and the libOQS crypto library. So what it does there is a weekly job, because these tests are a bit more time consuming to test all the implementations there. The C implementations and optimized x86 implementations, and it runs it as a GitHub action, right? That's a CI integration. There are, to avoid false positives, there is, Valgrind has the notion of a so-called suppression files, where you can explicitly allow list basically cases where like this rejection sampling that does not need to be done in constant time. So that's a nice tool, and there are quite some crypto libraries that uses this. Now the second type of leaks are because of compilers, right? If you write C code, you you try to make it constant time, right? There is still something between you and the machine code, which is the compiler, and the compiler tries to help you by optimizing code, right? And yeah, constant time code is not always the fastest one. Then the faster way is usually variable time. So that's definitely an issue. And yeah, there was recently there was a case that was found by Purnal, that he termed clang over, which was an issue in the decompression or implementation of decompression as part of MLChem or Kyber. What you do there is basically a naive implementation that you would see on the right-hand side is you take the message bits, right, shift them to the right, and if it's a 1, you set the coefficient to q plus 1 divided by 2, and otherwise to 0, right? Luckily, nobody does it like that, right? Because that's what you learn. You should avoid, right, to have a branch there. So what the reference implementation of Kyber actually did instead was kind of using some bit twiddling tricks, right? Where you, let's say, what it does here, it shifts the message bit to the right, which will and masks it with 1, and then takes the negative. So you basically have all 1s if it's a 1, and all 0s if it's a 0s, and then you can apply this as a mask to q plus 1 divided by 2. So that's only logical operations, right, which are fine, right? You don't have a conditional branch. And then if you want to compile this, it looks fine, right? So that's using Clang version 14 with OS flags. If you look at the assembly output there, it only has logical operations. So that looks very nice. But then what Purnal found is, okay, if you just update to Clang version 15, the compiler got clever, right, and detected, oh, that's actually, I can implement this more efficiently by making a conditional branch, right? So that's how it looks then, the assembly output there. And it contains a conditional branch. And the author there demonstrated that it was possible to do a timing attack and recover the key in about 5 to 10 minutes with MLChem 512, right? So yeah, so that's kind of scary, right? The compiler being smarter than we want. How can we detect that at least, right? And the answer, luckily, is that, I mean, also Valgrind can be used to detect this kind of issues, right? Just what we need is to have a very extensive coverage of a matrix of different compilers, different compiler flags, different architectures. So in the ideal case, with those configurations that we want to ship the software, right? And yeah, I mean, the example of libOQS, there was also a CV for that, is that the tooling, the Valgrind tooling there did miss the issue because the testing was using Clang version 14, which did not show this regression yet. So the plan is there basically to extend this, the tooling, and as part of the weekly build. I mean, there is an example, for example, there is one of the NIST signature on-ramp candidates, Mayo, includes also CI tests with Valgrind-based ones, and covers a matrix of about 102 combinations of different compilers, where always the latest Clang and GCC versions are used, because you assume, okay, compilers only get smarter over time, right? So you want to use it, and different optimization flags and code optimizations are tested with the aim to kind of detect these kind of issues. Which brings us to the last type of timing leaks, and that's about the more micro-architectural behavior. There it gets a bit more tricky, right? Because everything so far kind of assumed that all CPU instructions, they run in constant time, which is unfortunately not always the case. There are examples like older Intel Pentium 4 32-bit PowerPC architectures. The bit shifting there was not constant time. An architecture that is still used, right? The embedded MCU, ARM Cortex M3 integer multiplication there is not constant time. If you happen to use the FPU on ARM that with emulated FPU, that's not constant time. Then integer division in most architectures is not constant time, because implementing that in constant time would be quite expensive, right, to do. And there are other things, like there was a bug that was termed Hertz bleed, which uses the dynamic frequency scaling, like turbo boost on Intel, to leak some information. So the observation there was basically that the frequency scaling, so the CPU runs faster, dependent on the data, right? So something like if the Hamming weight of the data is different, it has an influence on frequency scaling. And the paper there basically presented an attack on, then it was the Cyc implementation that used these things. So these are all kind of things that are more microarchitectural behavior that should also be considered. Now, to also give an example about that, there was an attack that was termed, a recent attack also on the Kyber reference implementation called Kyber/, that was independently discovered by two teams. Dan Bernstein discovered it, and also a team making formal verification. And in this case, the issue was in the compression part, polynomial compression part. And what you see there is basically this line that was marked. It includes a division by Kyber Q, which is a constant like 3329. And yeah, I mean, if you write this, you kind of assume that in this case that the compiler is smart enough to see that, okay, and if you do a division by a constant, that's expensive. Better do a multiplication instead, right? Which is a very easy thing, right? And usually compilers do this. So if you compile this with like GCC 13 and O2 flags, you see there is no division instruction in there, but instead a multiplication. If you compile it with different flags, like OS size optimized, you see that there is a division instruction in there, which in this case is an issue, right? Because it's about secret polynomial coefficients. There was a paper about Kyber/ published that showed that this could be used to do a key recovery on Kyber 512 in 2 to 4 hours on a ARM Cortex A7. And I mean, interestingly, this was first discovered using formal verification, where a team did a F* formally verified implementation of Kyber. And there you can have this, they have something like they define as part of the types, kind of secret data and public data. And if there is secret data, you don't have things like divisions available. So this could be detected there. So that's definitely one interesting tool in that case. But formal verification, it's not an easy task, right? So if you have a software implementation that is not formally verified, how can you test such an implementation there? So there is tooling available to do something like that. I mean, the example I have here, it's a tool called DoCT. So it was from a paper called Do This My Code Constant Time. The idea there is that you basically want to do a statistical test. So you run the code with different inputs, with a control group of a fixed input and a test group with a variable input. You pre-process the data, and then you apply a statistical test. In this case, it's Welch's t-test, where you basically want to reject the null hypothesis, where the null hypothesis is the two timing distributions are equal. And if you reject it, you can say they are not equal, so there is a timing leak. Now, as always with statistical tests, you can only reject the null hypothesis, but not prove it, which basically means that there can be false negatives, right? For example, here with this, we could run this on a Raspberry Pi 3, right, which has quite differences in cycles in the division instruction, while on an x86-64 it wasn't that straightforward. But on the right-hand side, you basically see how the tool looks, right? So you run a vulnerable Kyber decrypt implementation, and there are different metrics there, but the t-value, if it exceeds a certain value, you can reject the null hypothesis and say it's not constant time. While if we move on to a fixed version, and if we run the tool again, it will basically run the tests again, right? And the t-value ideally won't exceed the threshold, right? And I mean, the tool recommends that you run it for like 120 seconds. So something like this could also be used in, let's say, continuous integration, because we think it's kind of important to try to detect these issues early on, right? And in this case, this is a GitHub action that runs this Kyber decryption. So the runner runs on a Raspberry Pi, and the tooling detects this issue, right? So this could be integrated in a CI toolchain. Now the authors of Kyber/, they also proposed a patch to Valgrind again, where some known variable time instructions are flagged, right? But I mean, also there would be limited to these instructions that are flagged. And of course, if you only have grep available, you can also use grep to do that, right? Which was actually the first, I think some people did then when they wanted to test their implementations. Also, with this Kyber reference implementation, it found its way into many downstream implementations, right, that needed to be fixed, right? So, which brings me already to the last slide, right, about some conclusions, right? Like if you implement cryptography, need to be very defensive, right? And also need to be aware that, let's say, just standard ways of not doing conditional branches is not sufficient, right? Have to be a bit, some sense of paranoia about what the compiler can do is necessary, right? And you need to do some more work than just writing code that looks constant time. Also, one thing is that usually assembly code is a bit less susceptible to timing bugs, just because there isn't a compiler in the way that could optimize things away. Also, I mean, writing assembly code is difficult, while it's not as straightforward and it's not as portable. And I mean, one example in the liboqs library, we have the implementation for Kyber, which is a formally verified implementation using the libjade project, which actually generates assembly code and has some of these, for example, there are guarantees that there are no divisions in there. So formal verification can definitely help with the correctness and timing to write timing-resistant implementations. And finally, I mean, as always with testing software, coverage is important, right? Not only covering the code, right, but also covering the context and the platforms, the architectures, the flags and compilers that you are using, right? And yeah, I mean, and with the examples of tooling available that can be integrated into a CI, right? I think it would also be nice that more and more of this testing moves into the CI, in the CI pipeline, right? To be able to detect it early on, because otherwise it's more like you write code and then you you analyze it later once, right? A couple of times, right? It's not that, so to have kind of a shift left paradigm also in writing crypto implementations, right? It will not detect all the issues, right, in there, but it certainly can help to avoid some of the issues that were outlined here. Okay, here are some references to the tools. There was also a nice usability study published for different constant time toolings and some attacks that were covered here. So thank you very much. I'm open for questions.
Any questions?
So a quick question about one of the test results that you had. Where you did the statistical testing, and it seemed like your test results could depend on your actual test vectors, where you had a standard set and then a kind of different variable step, and I guess one was your control and the other one was what you kind of did your rejection against. But it seemed like that one, if it wasn't right, you could get false positive. Could you talk a little bit about how you might avoid that, or how do you get test inputs that might give you a better result consistently?
Yeah, I mean, one aspect is kind of the platform you run it on, right? If there is noise and so, you can have false positives or false negatives, and the other one, doing the right test vectors, which a bit depends on the scheme. I mean, this case, it used basically, the decryption API, right, where you can basically have one control set, right, where you, in this case, it's always randomly generated, right, the control thing, and then you modify it, right, and to have the random group, right. In this case, it's not specifically crafted, so, but it seems to work quite okay, right, even then, but right, if you think about things like if you want specific tests that cover certain parts of the code, I think that's probably something to consider,
Chris Seeley with the Cryptographic Algorithm Validation Program at NIST. So essentially, we have a system that can generate test vectors for black box implementations. One of the things I'm interested in is doing that, offering test vectors specifically crafted for measuring timing data on implementations, and offering, a gold star or something on an algorithm certificate that meets certain timing assumptions as a result. I don't know if I'll boil down to a question here, but thank you for this presentation. I'm interested in exploring some of these ideas. I might be reaching out to you on some of that, so thank you.
No, thank you. I mean, specifically crafted test vectors, I think they would generally help to have some even better coverage, right, to detect things like if you have, probably you want to provoke certain corner cases like number of rejections or something like that, and I think that would be really interested to feed in some tool chain like those.
Unfortunately, because we are black box testing, it would be up to the lab or the implementer to run something like DudeCT to get the data back, but that could be passed back to the server and verified in terms of yes, they ran this set of tests to arrive at a constant time assurance or something of the sort. But that aside, very interested in exploring this work in terms of an algorithm certification process. So thank you.
Thank you.
So thank you very much for the talk. Something that occurred to me was we're about to get Falcon coming down the pipeline, and the first thing everybody says about Falcon is, and we're going to break out the floating point arithmetic for this one. This is a part of the instruction set that cryptography has never really sort of touched before. Do you think it's going to be something we can take in our stride based on the work you've done here?
Yeah, I think that's a very good point about Falcon, right? It uses, at least the signing operations, uses floating point arithmetic. which, yeah, I mean, if you go like to embedded platforms, it's tricky, right? I mean, there are ways to replace the floating point arithmetic with purely integer implementations, which come with some drawback. And yeah, but I mean, yes, I mean, like in libOQS, there is also a Falcon implementation in there where the tooling runs on. There isn't yet something like DoCT, but I think it would be interesting to apply that as well to this. Yeah, thank you.
Let's give a big hand to Basil. The next one is a panel, but the panel leader, Ralph Poor, is he here? Ralph? Are you Ralph?
No, I thought this was Ryan Hurst.
I'm sorry?
This is not the cryptographic inventory.
This is panel is on status of cryptography security standards. Oh, okay. So whoever is the panel lead, are you the panel lead? I'm sorry, I was going by this. All right. So, I know your name.
Ryan Hurst.
Ryan Hurst. Yeah. So Ryan Hurst will be the panel lead for this. Sorry about that. And he will take over from here. And just before I hand over the mic, I want to just remind everyone that today at lunchtime between 12 and whenever, 12:15 and 12:30, please pick up your lunch from downstairs or eat your lunch downstairs and come up to the next room. That's where the Cryptographic Module User Forum, CMUF monthly meeting would be. And that would be for 45 minutes. So please, if you're interested, please do come there. All right. Thank you. Please give a hand for.
No worries, it happens. If my panel could join me. This is Lily. Yeah, we're down one. Doesn't matter. Take a seat. Okay. We'll give a few more minutes to make sure that everybody's here. Just thank you for your patience. I know. I understand. I'm looking for the other panelist. Well, we'll get started, I guess, then. Okay, so, Lily? Yeah. Yeah, thank you very much. Well, while we wait, my name's Ryan Hurst. I'm an advisor to SandboxAQ, and I've been in this space for about 30 years now. I look around the room and I see some familiar faces I haven't seen and some new faces, so it's a pleasure to be here. Today our panel is on getting the most out of your cryptographic inventories, and we have some great speakers that I have the pleasure of introducing shortly. I think this is a really interesting time for us as an industry. Having been in this space since the mid-90s at least, the idea of having a cryptographic inventory outside of an individual system is actually pretty novel if you were to look back at that period of time. And now we're looking at this Cambrian explosion of cryptography as more and more systems become distributed systems and every system begins to consume cryptography. And that creates this interesting opportunity that we can now start to use this inventory of the way cryptography is used in an organization to turn cryptographic key management into actually a risk management function rather than sort of that tax that we have to do when we are managing systems that happen to use cryptography. That is something that is pretty novel and is starting to prove to be really important. We've got, over the last year, a number of interesting situations where vulnerabilities were exposed due to poor cryptographic key management practices or even weak cryptography, which in itself is very rarely used as the attack vector, but now is increasingly starting to be found to be an Achilles heel of systems. And so that, combined with our future migration to post-quantum secure algorithms, gives us as practitioners in this space a excellent opportunity to start driving changes in the way we build our products and the way we manage the environments that we're associated with. So I'm very happy today to be able to have the three panelists that we will have, all three, I'm sure. Yeah, I unfortunately, I'll take it down, I'm sorry. Yeah. Very happy to have these panelists with us to talk about how they see this playing out in the industry. And so I'd like to first start by introducing Victor Mateu. He's the acting chief researcher at Center of Technology Innovation Institute in the UAE. Victor, would you like to talk a little bit about your role and how that intersects with the topic today?
Sure. So I had the opportunity to talk about cryptographic asset inventory, especially pointing at the migration to post-quantum. So that was the main focus initially. But I think by talking with different entities, public and private entities, we have discovered plenty of use cases in which having the inventory will play a key role in the risk assessment for different companies. And basically, I think it's important to showcase this and to share the information. So yeah, that's the experience that we have on it.
Thank you, Victor. We also happen to have Dr. Garfield Jones, Associate Chief Strategic Technology for CISA. Dr. Jones, could you talk a little bit about how CISA's and your role is intersecting in this space?
Yeah, so thank you. So it's CISA is looking at it, of course, from the whole pessimistic side of there's bad things that's going to go on with quantum, and so my role is basically looking at all emerging technologies, which includes PQC. We're very worried about a CRQC or cryptographically relevant quantum computer actually compromising all of our PKI, and that could be very detrimental to the government. So they tasked me with looking at this, not only looking at that, but looking at the PQC part of it, but seeing how it ties in with other emerging technologies and how they can be affected by the advent of a CRQC.
That's great. Thank you, Dr. Jones. So my favorite panels are ones that sort of evolve into conversations. And I think one of the things that's interesting about this group is that the people in this room are actively doing work in these spaces. So at the end, of course, we'll have a Q&A, but I also am looking forward to asking those in the audience what they think about this space. And so as you hear the dialogue today, keep that in mind, and we'll hope to bring in some of your thoughts at the end as well. The first question that I was hoping to talk about today is misconceptions about this topic. This is a relatively new concept in industry, and we see it evolving a lot, and we see a lot of different positions taken. So starting maybe with you, Victor, do you have any thoughts about misconceptions that people may be having? Actually, one moment. We'll give Lily an opportunity to come up as well. Thank you, Lily. Oh, no worries. I've done it. I first met Lily certainly by 2000, back when I think she was relatively new to NIST. And so Lily, why don't you talk a little bit about your role at NIST and how that intersects with this topic.
Hello, sorry I'm late, and because of 15 minutes shift, I didn't realize. And my name's Chen. I have been with NIST for 19 years. We are working on the cryptographic standards, and between the 2012 and the 2023, I was a cryptographic technology group manager. And then since 2023, I become a NIST fellow, and I look into the different initiatives. One of is, besides the PQC standards and other cryptographic standards, and crypto agility is one of them. And we work with some collaborators in the NCCOE migration to PQC project. So my current role is to look into these initiatives.
Thank you very much, Lily. That's very relevant, and looking forward to your conversation today. So Victor, coming back to that question, so what are some of the misconceptions you think that exist in this particular space?
Yeah, so lately what I'm facing more when I'm talking about pushing the idea of trying to come up with a cryptographic asset inventory is the idea of what is a cryptographic asset. So some people summarize it on, okay, I'm using TLS. It doesn't work?
I need to speak. Okay. Okay.
So basically, because of that, we find that every company, every institution have its own understanding. And I think that the name of cryptographic asset inventory is actually a very generic name, but it's hard for companies to understand when they have never been exposed to it. I think this misconception will be clear the more we use them, but nowadays mistaking cryptographic certificates as part of the cryptographic inventory, mistaking programs or cryptographic libraries. Someone says, okay, I have OpenSSL, and it's like, but the important thing is how are you using the library, how is it integrated? And this is something that we see more and more, but I think the more the technology matures, we are going to start focusing on the right points and let them people understand and push forward to the right directions.
That's great. Lily, how about you? Any thoughts about misconceptions you see in the context of cryptographic inventories and CBOMs and how products and organizations adopt them?
So in the last 5 years, I was often reached by different government organizations, other agencies, and they would like to ask me to give a talk about PQC. So the first thing I would ask, to whom? So I think the inventory, the cryptographic inventory, also include the inventory about the management, especially our upper management understand how how their personnel manage in charge the cryptography usage in their IT security applications. Often, this question cannot be answered very well. They say, oh, we have a committee, and so I ask them how you use cryptography. They cannot answer. I usually will say, okay, well, I can give a talk on the PQC, but I really like it to the people who really in charge about cryptographic usage to come to my talk. So that they feel very, yeah, we didn't think that way.
Yeah, no, I agree. Dr. Jones?
Yeah, so from my end, I have to agree with Lily on that. Some part of the management, you try to talk to management about this, and they look at you like, why? I've got like 10, 20 years, and they're not, focused on it. And there's like, why do I need to dedicate resources to doing my cryptographic inventory when I've got 10, 20 years? And you reference Moscow's timeline, and you're like, hey, look, we're already behind, we're in trouble. So I think in that sense, management has that timeline misconception. Also, on the inventory side, we think that one tool will be that silver or that silver bullet, and be like actually able to grab everything and inventory everything. So we definitely have that. You know, I've talked to some agencies and they're like, well, I can't support you know, a suite of tools or you know, a collection of tools. I just want one tool to do it all. And we're like, well, good luck. You know, there's nothing out there that can do it. We haven't even proven that a suite of tools can actually do it. So there's a lot of misconceptions that one tool can fit all. And then lastly, the CBOM. I think you asked about that as well. And you know, the cryptographic bill of materials, I think a lot of misconceptions are there. People see those as almost standardized, and they're really not yet. You know, we're not there yet, and so we have a little ways to go before we get to actually standardizing and getting those elements in place to get a decent CBOM. So I think those are kind of the areas I would see as true misconceptions.
Yeah, I'll add one is that inventories are a one-time activity. I actually think that there's two sets of, there's this whole proactive inventory that you see would be happening inside of your software ingestion pipeline, and then your periodic assessments via these, what are oftentimes expensive to operate at runtime discovery tools, is you really end up having to look at this strategically about the way you use software. So for the second question, I thought it would be good to talk a little bit about what are some of the challenges that we have about getting that comprehensive inventory. Lily, would you like to tackle that first?
Actually the challenges, I think the first, because I want to let everyone know, if we haven't covered that, the NCCOE project migration to PQC has some deliverables. One of them is 1838 serials of the publication, and 1838B is about cryptographic discovery. So that means to do the inventory to discover where you use cryptography. Because today in each of the enterprise, really cryptography has been used in everywhere and in different ways. So I think the most kind of challenge part is some of the things is we got that as a black box. Right? For example, we purchase third-party software. That is a black box. You don't really know what cryptography is inside. We have input, output interface to connect the API to connect, but we really don't know. And also now the cloud computing and added some burden to do the inventory as well, because sometimes in order to interoperate with the cloud storage and things, you have a lot of crypto usage you may not really understand. So that's how I see the challenge.
Yeah, I agree. Victor?
I completely agree with it, and I would like to extend it into what I consider the phase of uncertainty, which is, for me, the biggest challenge is the fear. So people doesn't have fear of what they don't know they have. But imagine that you are running your company, all of a sudden someone tells you, okay, run a cryptographic inventory. You find 7 flaws, but you just discover that you are powerless. Like you were mentioning, you have so many things that are like a black box. You don't have power to change anything, and all of a sudden you just have a list of vulnerabilities, a list of issues that you cannot go to management and say, okay, I want to change it. You are just basically powerless, and it basically highlights a lack of capability. I think that's something that it's trying to be protected by companies, and I think it's the opposite mentality of what needs to be done. I think cryptographic asset inventory is an empowering tool for a company, and it gives the right to say, okay, I know what I have, I know how to move forward, and I identify the caveats that I am having in terms of capability to migrate, to prevent, and to patch things that I have on the company. So I think the main challenge here is to find a proper path to know what to do with this cryptographic asset inventory once you have it. And I think fear is the most deterring part now, and I think that should change. I hope bringing to light the problems pushes forward on this direction.
I totally agree. I actually think a good example of this sort of being constrained might be this PK fail issue, where you don't have the ability to redeploy all of your hardware because and keys being exposed. And this is a good tool and opportunity to hold vendors accountable in the purchasing cycle. Dr. Jones.
Yeah, I think I absolutely agree that that's a great thing about going last is that you can disagree and move on. But I think from the government's perspective, I think validation is the other piece to it too. Not only understanding, but having that validation portion of it that the crypto is in there. So we're looking at it in terms of a lot of people don't understand that. Because you have that black box, they assume everything's working and everything's good, and they don't have to worry about it. But we've been operating in that black box for so long that it's actually made us I guess you could say just not aware of it. Mm-hmm. And it's so the understanding is having that validation, being able to show that, hey, this is working. We can see this. This is what it looks like when it's not encrypted. This is what it looks like when it is encrypted. I mean, I think it's very similar to when we had when the S appeared on secured websites, and you were like, oh, well, now I know I'm supposedly secured with the S, but we don't have anything like that on the crypto side, at least not that I know of. I'm not a cryptographer, but I think that's something that will help folks understand a little bit better of what's going on in that black box.
I like how you touched on verifiability. I think, or verifying just in general, it's something we don't talk enough about when it comes to claims from vendors. Years ago there was a video conferencing application that said, hey, this is all end-to-end encrypted. But that actually meant they were using TLS. Mm-hmm. A recent compromise of a power system. This is all securely deployed, and 512-bit RSA key, if I recall correctly, was part of their definition of secure. And so, like, being able to verify the claims of and the absence of claims of what software and services we rely on, to your SaaS comment earlier, I think is really important. Another question we thought might be interesting to explore here was how can organizations assess the right tools for their specific environments? What metrics maybe should be used to measure impact, or how important is it? We've already talked one tool is probably not enough. So maybe we can talk a little more about that. We'll pick on Victor again.
So actually, it's good that you mention it, because when talking about the challenges, I mentioned the one that I consider is the strongest in my opinion. But certainly, the tools that you use to detect in your infrastructure are also one of the problems that we will face when we try to do cryptographic asset inventories. Like the deeper you go into your infrastructure, the more information you can gather, and the more power you have. So if you want to get information about how is TLS set up, maybe you can do it in a passive way. Maybe you can have like binaries inspected. Maybe you can have like a traffic inspection. But how will a company operate and allow traffic inspection and all the certificates that are involved? How you make actually your infrastructure less robust? That means that you need to have like a space where you can test this separately from your operation space. And all of this is added complexity into how to run an inventory properly. Now, the more we want to have information about this inventory, the deeper you need to go into the trust or the effort to deploy an environment where you can actually discover things. And I think this is basically the second challenge that is there, is how a company can all of a sudden come up with a solution when just 5 minutes ago we didn't even know that we needed that. So that's the main point for me for this.
Yeah, I'd keep you from being at the end again. So how about we pick on you again?
I have no problem being at the end. I'm very agreeable. But in terms of what tools, how the organization measures that and everything, I think when an organization has to measure the tool set and all that, I think you have to look at, is the tool, I mean, we have the OMB post-quantum report that came out, and it basically stressed manual inventory. And that's fine. We can do manual inventory to lay a baseline, but then we have to do automated tooling because the manual inventory is not going to keep us, it's going to slow things down. And I think one of the metrics that you measure for an organization on this is how does it impact operations? And if you're slowing down operations because you're like, hey, hold on, I got to count this system, so shut it down and everything else, and you do all that. I think these are areas that you really have to be careful of. Does a tool prevent you from getting your operational impact that you need to get done? So I think that's one way. Of course, once you get operations impact, for any organization, it's money. How can you measure? Are you making money? Are you losing money? Is everything slowing down? So time, costs is one of those areas that we really have to look at to see how those tools really address what we need in the organization.
That's great. Lily.
This is, I think, in order to get different tools, I think the collaboration is very important. So the NIST NCCOE has a collaboration program, and I think this is really critical to find different tools and to use different tools and to see how we can put things together.
I agree. One thing that comes to mind listening to each of your answers is this metrics topic. I think we often struggle to come up with business justification to be able to do the improvement work that's necessary around cryptographic key management. And the hard part is usually getting that whole number. And while I don't think any cryptographic inventory will necessarily give you the true whole number, it does start to paint a picture of the size of the sort of what's load bearing with cryptography in an environment. I think it'll be a very useful tool for ensuring future funding for organizations that take the time to make these investments.
That's an interesting point that you brought up about the funding. I know we've had a lot of discussions all over about how to fund this, and that's going to be, I think, one of the biggest hurdles that we're going to face, especially when it comes to implementing tooling, because I don't think organizations have laid out that funding yet.
Yeah.
And that's one of the areas that we need to start talking to our senior management and saying, let's hope that you're putting some money away for that migration and that tool set as we go forward, because that's where things are that technological surprise. We all got a little bit of a surprise with the LLMs coming out and everything else, and everybody was struggling to get policies in place. I can't imagine if it's well, all your business is out there and all your data is out there, and people, we haven't talked about the harvest now, decrypt later. Mm-hmm. So how are we going to fund that? And management isn't always thinking about that in the sense, and it's our job to bring it to their attention.
I think this is where we have that opportunity. Actually, C-bombs are interesting. I've been somewhat critical publicly about S-bombs for reasons that is a hallway conversation. Yeah. But I think the criticisms of S-bombs don't really apply so much to C-bombs, in that there is actually something actionable you could do with this information. When you see that you're using OpenSSL with this particular suite, you do actually have a lot of actionable decisions that you can make in regards to how you manage your vendor relationships and changes. So I think that getting the cheap way, coming to how do we afford to do this, software ingestion is probably one of the cheapest hooks organizations may have to get their first inventories. Lily, what regulatory guidance does the U.S. government provide to agencies regarding this? So we've touched on it a little bit, but maybe you could talk a little bit more about the 1838B or what's happening in CCOE?
So here in the audience, I already saw some of our collaborators. You are very welcome to weigh in about this 1838B. And I already see some people smile face, and so you can come to that. So in general, this is a kind of deliverable. First is we have a very clear purpose to migration to PQC. So however, the inventory is not limited just for the PQC migration. And this document talk about challenges and talk about some use case. That use case are very, very interesting, I think, to see in different situations. That's why one tool is far less enough. And also some other strategies in this document. So this document, I think, will serve as like a framework for people to talk about inventory. So that's my understanding about 1838B. So anyone want to chime in? Muruja, do you want to talk something about 38?
Don't hide back there, Maruja. We see.
Yeah, so I'm Murusha Supaya from NIST. I co-lead the project, and Gary is also on the project with us. I see a lot of other collaborators in the room as well. So our goal with the project is, as Lily indicated, is to identify some of the use case. And in particular, we're working very closely with our colleague from CISA to understand what are the US government kind of use case, so that we can build out these example environment in our lab to be able to use diverse type of tools. One tool is not going to be able to support everything. So we're looking at this from a network discovery perspective. We're looking at this from a endpoint device, containers, virtual machine kind of perspective, looking at API call, looking at libraries that's loaded on the device themselves. And then last is if you're actually a developer and you have crypto in your code, we also want to look at a set of tools, as part of the CI/CD pipeline, be able to identify that. So using a combination of those components is going to help you reach this kind of visibility and understand have a complete inventory of what you have across your environment. We are not going to pick winner or loser or anything like that, but it's more about defining the capabilities of the tools so that stakeholders would understand when to use what type of tools and so on and so forth. So, Gary, maybe you can...
I see how you sent that back. Okay.
Please.
Yeah. So yeah, we're working, as Maria was saying, we're working very closely with NIST on this, and we provided some use cases to them, and our focus is to try to cover the gamut of systems, where we're even talking about some critical infrastructure systems, the OT, and maybe even get to some of that. But when Marisa was talking about, the one tool is not going to fit all, I think you have to look at the federal space. In the federal space, we have federated and non-federated, and we have state, local, tribal. We have such a diverse set of agencies, and not only that, but these agencies don't just interact with themselves; they interact with the public. It's not like DoD where they can say, okay, all .mil do this, and yes sir, and you go out. But with us, it's like, okay, now your IRS has got to interact with your public, the Commerce, the VA. So we've got to be careful what tools we use in those spaces, because they will affect, as I said before, the operations of it, and then so that's why we're working very closely with them, trying to provide them as many use cases as we can. We've got some more for you coming.
Victor, we had an interesting conversation in the hallway kind of related to this about what's happening outside of the U.S. and how everybody is sort of trying to collaborate with each other. Maybe you could talk a little bit more about that.
Yeah, actually, I wanted to mention on this line that, okay, the US have all these platforms to showcase how to do it, and there's a whole process and institutions there. But on our case, and it's also targeting the idea of the cryptographic asset inventory, we are trying to push for the migration, but we don't want a full migration. We don't want to migrate signatures, for instance, now, because it will be harder for them to adapt. The complexity of doing it against the risk is something that we value very much, and we understand it's harder to do it. So what we are trying to push is a migration plan, and in this migration plan, we always recommend cryptographic asset inventory is a first phase always. So don't try to do it by your own. This is not a good idea. Try to have an asset inventory, but especially and this is the part that we are crafting, choose the specific assets that are communicating. We don't care that much if you are doing like a storage in your organization with something that is not quantum resistant. We understand that that might be the case, but the problem that we are trying to tackle is it's a store now, decrypt later attack. And storing now is usually on the communication. So if you have the cryptographic asset inventory tool, you can target specific things for each of the regulations. It can be adapted. So all the vendors can actually help and collaborate on saying, okay, I understand that this rule says, okay, A, B, C, D needs to be evaluated. So let's focus on this, let's do a report, and then everyone can plan ahead. So I think this is a cornerstone of how one tool fits multiple purposes. It's not only one country, no, the tool can actually accommodate for the different countries and also accommodate for the speed that they can allow. So the US can allow for a faster speed to migrate, but that doesn't mean that others don't need to have an inventory of what to migrate and why is it like a higher priority, lower priority. All of this can be part of the asset inventory tool, even more like automated things on it.
Absolutely.
And I remember you asking about the regulations. So we have OMB 2302 that basically told all the agencies how to do their asset inventory and focus on the high value assets. So that was one of the main things. We have other draft, I don't want to say regulations, but we have other draft policies coming out that will kind of reinforce that. And I think that NIST working on it's a draft 1800. It's in draft stage right now, right? Yeah. So I think that's going to help us out as well. So the government is taking this extremely serious and wants to work with everyone. So on this and trying to make sure that we're getting the right tools into the right environment.
That's great. So another area that you can't talk about cryptographic inventories and not touch is the topic of agility, and some interesting hallway conversations around how the definition of agility is quite subjective, has also changed over time. So Lily, I guess starting with you, how can these inventories be structured to support an organization becoming more agile for some value of agile?
Yeah, well, yesterday we had a panel on the agility, crypto agility, and so this is closely related to the inventory, because right now, we have a lot of situations when we think something is broken and we need to deprecate some algorithm, and people don't know where those algorithm is used. Is that this? I can give you example like the similar situation like a manufacturer recall food or something. You don't know that is already in your pantry. You still continue to let your kids to consume those the snacks or something. This could be very high risk. So in order to make the crypto agility, the basic is that you have a very clear understanding what you are using today, what you can move to and you cannot move to. So these two topics are very, very closely related to each other. I would like to say that the inventory is critical for the crypto agility. Otherwise, you don't know what you can do about agility, what to move out, what to move in, and how to switch. So that's what I can say.
It sounds to me, I could summarize that as, you don't even know if you're agile if you don't have an inventory.
That's right.
Yeah, and that's I think that's a really simple and strong message. I agree. Victor.
Yeah, whenever we have this conversation about crypto agility and how the whole idea of the asset inventory plays into it, I kind of always resemble this, this in the wall of like fitness and all of that. There is these guys that do only upper body, and then the down part looks like thin. So I have always the same idea, like, okay, we have all this idea on, okay, I want to migrate, I want to be able to be agile, I want to be able to move my asset, I don't know, I have TLS, I want to be post-quantum, then there is a standard going on, I will be able to migrate. However, you only will be able to migrate what you see. And most likely, underneath, what will happen is that you will be extremely weak, and you will have one thing that is post-quantum but how many of your communications are going to be protected by this? I mean, with TLS, I mean, fortunately, hopefully with TLS, we are covering a lot of them, yet you will not know what you don't know.
It's almost a cheap way to get, like, calling it a threat model is too generous, but it does give you indications of where you might want to dig in deeper.
Yeah, exactly.
So on crypto agility, I mean, that was funny. Sorry, I got a picture of this huge guy with these two sticks for legs. I'm just like, okay, I'm just trying to come back to my answer. But the point is that crypto agile is not only dependent on just the inventory, but I think it's dependent on the vendors as well, and being able to build that into the architecture that we have, and being able to transition to there. I think as we go for more, and this is where we go back to the C bomb and the S bomb and things like that, understanding what's in there. I think and I hate to mention it, but I'm going to mention it. Secure by design. We have to have that kind of mentality when we're talking about crypto agile, because if we're not able to switch and the products that we bring into our environment is not able to flip over, that's going to be a true problem for our organizations. So crypto agility, I think you have to know what you have in there, but you also have to know what you're bringing in there, and does it mesh well with your architecture, and is your architecture dynamic enough that it can say, okay, if one of the, Lord forbid, one of the NIST algorithms are broken, how do we switch over to something else? So I think that's where we really have to be working with our outside vendor, and really have to take a look inside and see is our architecture that we're planning, can we migrate over it with just what is one dynamic tool attached to these other static tools look like, and then it would be able to do that. So security architecture is going to become a really big part of this.
Listening to all three of your answers, actually across the preceding questions as well, it starts to feel like maybe there's an opportunity for a maturity model for how well an organization manages cryptography. Mm-hmm. And I would think that a cryptographic inventory would be one of the baseline elements that you would see in an evolving organization. And having the infrastructure in place to be able to hold vendors accountable, coming back to those cloud providers and the vendors who I can't do anything with them because that's just the way the software works. That's the only way we'll get to be able to solve these kind of systemic problems that I'm hearing. So that's really useful. Thank you. I think we have time for one more question before we go to question and answers. In particular, we had talked a little bit about NSM 10, the National Security Memorandum 10, and how agencies need to be ready by 2035. Maybe, Dr. Jones, you could talk a little bit to that and how that might pan out.
Yeah, so the NSM 10 really kind of kicked off all kind of put all the agencies on notice that 2035 is when we have to migrate. But at CISA, and we recommended this to all our government counterparts, is that you plan on 2030. There is a lead time, and there's a fine-tuning time that you have to worry about when you're getting to 2035. And 2035 is migration of all the systems, which you have to make sure that you're on that path. So we planned from 2030, right? So that we can do that. NSM 10, there's a lot of collaboration between OMB, NSA, us, other agencies, DOJ, FBI, just to be able to understand what does it look like to move over to this PQC. And it's a difficult thing, for agencies. We've all got, these varied networks, and we've got our own customers to deal with. And so it gets to be a difficult thing, but 2035 is coming up very quickly from our aspect to migrate about 100-something agencies. Not an easy task. So that's why we're planning. There's one thing I've learned about the government. They're like my brother, right? Every time I invite him to a party, I tell him 4 o'clock. He shows up at 6:30. So I've learned that you've got to tell him 3 o'clock or 2 o'clock, so he comes at 4 o'clock. So the government's the same way. You tell him 2035, you really need to tell him 2030.
Yeah, no, that makes sense. Lily, NIST has played a really important role in getting us to the point where something like NSM-10 was even possible. What are your thoughts on this topic?
Well, right now because after we published the first set of the PQC standards, we started to think about, because we have this 90-day kind of action to generate a guideline about transition. And the very important, because in this community, for this conference, people were all concerned about when NIST is going to deprecate that the classical public key cryptography, right? That's all the people think. When the FIPS 140 validation will stop to validate RSA, validate ECDSA. This is the question. So we are very much aware that 2035, this timeline. So the first step, of course, we encourage people to adopt PQC. Once people adopt the PQC, we will have a better understanding about how the PQC works in the real world, in a large scale of the real world. And then we can have something step by step to make that transition. And the second is that we wanted to look into the interoperability, because right now we don't want to, well, not that we don't want to, nobody can shut down the internet for 2 minutes, right? So you don't have that kind of luxury to stop things at this moment. So we will consider interoperability. For both of this, we will also seriously think 2030. But Dr. John said that yes, 2030 35 may mean 2030, right? That's something we are thinking to step by step to deprecate public key cryptography. But right now, we don't have a date yet.
Victor?
We work to find a date.
Any thoughts on this topic, Victor?
For me, I can only thank you guys, both of you, because I think all the effort on doing this and pushing it at this stage so early from the big institutions, it's also a recommendation for all the rest. And I think the fact that you say 2035 here for all the rest means, okay, 2035 means something. So all the rest of institutions worldwide will try to push and understand that there is a movement ongoing. I think that makes the effort of all of us here trying to push for cryptographic assets, post-quantum cryptography, it makes it way easier. So yeah, I can only appreciate what you guys are doing here.
Yeah, I want to stress the same. I can't, I think one of the misconceptions is that, this whole problem of migration is new. Another is that it's a one-time effort. But having been in this for a while, this is, I don't know, the 6th sort of migration-ish that we've gone through. And what I think is interesting about this one is how proactive NIST has been in this particular one, and the US government in general. And when I do speak with people from other legal jurisdictions, half the time they simply want to know what's happening with the US so that they can push the same thing inside of their organizations and their countries. So I personally am very thankful for the work that you two have been doing, and others in the room. So given the highly technical nature of this audience, I thought it would be really good for us to have a Q&A session at the end. I know that's common, but if you also have thoughts on this topic that you think would be of value, we'd love to hear those.
Hi, it's John from Interest. I was thinking when Maruti was up here and he mentioned about, having like a CICD scanning tools that, detect these things. And like I know we already have that. I mean, probably most organizations have things that scan for vulnerabilities. So if these like PQC algorithms, you know, were marked as vulnerable, right, then they, tools that people already have integrated in their pipelines and that would just be able to pick that up or match against a database. Just wondered, I was thinking about, or maybe there are already vulnerabilities for those, I'm not sure, but I just wondered what your thoughts are on that, because I think a lot of those tools exist today, and maybe just, you know, we know these algorithms are going to be deprecated, they need to be deprecated, but their vulnerability, we know they're future vulnerable, right? So just marking them as vulnerable now could help tools that exist today already detect. And then that could be used, you know, to determine, you know, to create that inventory of what is vulnerable versus what is not. So just wondered your thoughts on that.
Any thoughts on this? I always have opinions.
No, go ahead. You can chime in first, and I'll chime in.
So I've spent a lot of my time in large software development organizations, and we are starting to see existing tools have, you know, basic checks, for example, looking for SHA-1. It's about time. But they do definitely catch these things, and more modern tools are starting to look for leaked cryptographic keys inside of software, and cryptographic, you know, weak primitives like IV reuse and basics like that. There's also, of course, specialty companies like Sandbox that specialize in finding lots of cryptographic foibles and all of the weak cryptographic usage patterns inside of software. So I think we're going to see more and more of that. But I also think we're going to see these specialized tools continue to get better at making the information actionable. And I think that's the big problem, is alert fatigue when even in these vulnerability tools, is how do I know if this matters? And that takes expertise, and I think that's where these more specialty tools will probably fit in.
Just to add on to that, I think you know, it's not only just finding the right crypto in there. I think you're going to have to do some kind of risk assessment, and I think risk assessment tools are going to be another piece of it. Understanding not just, you're going to have to tie that in with your data and see where that matters, because again, it's a harvest now decrypt later issue. So I think all of that is in, you know, as Ryan's saying, that as we move towards more knowledge about this, the tools will get, I think will start to advance along with that, to include the risks to an organization based on their operations.
Sir.
We are kind of inventing the next cutting edge PQC algorithms right now, and we are testing them right now as we speak. So, I mean, NIST is sitting at the selection process right now. All the 4 algorithms that I have seen in last 3-4 days and experience, like they are emitting like huge public key. So moving ahead, I think when we are testing these algorithms, speed is going to get hurt. I mean, the larger the key, the speed is going to be a problem. So when we are testing, we don't want to feel that we are coming to the dial-up age, right, in 2035. So can NIST put a restriction on how big a public key should be? I mean, are you going to accept like 3 terabyte public key? No, right? So right now, I mean, it's emitting like huge public key, which is going to be a problem. So can you put a restriction like any algorithm that you submit has to have a limitation on how big a public key can be?
I don't think that's necessarily the direction that we would go. The U.S. is very careful with, regulating. I would say, dropping regulations on limitations of technology, and we're very careful on that, because we also know that technology changes, and so I understand you saying that large key might just really destroy some things or slow down some things. Is that the question? But then we're also looking at computing power and everything else that's starting to progress. So I mean, will it limit an organization? So you drop a regulation on that, then something happens, now you got to change the regulation, and what do you change it to? So I think right now, I mean, not that I know of, there's no plan to regulate the size of public keys.
I'll add a little bit of color to that, in that Victor and I had a conversation in the hallway a little bit earlier about how we've evolved our thinking about the way we design security protocols. The formal modeling wasn't really a thing, 20-something years ago. And we've learned a lot about where vulnerabilities kind of lie in between the cracks, and protocols get designed differently now. They tend to incorporate cryptography natively rather than having it being bolted on after the fact, and try to achieve authentication through every step of the protocol rather than just at the beginning and the end. And so I think that what the relevance to your question is that we're going to be designing systems differently for post-quantum crypto than we will be, than we did 20 years ago. And so we're going to go from a world of one asymmetric algorithm to choose from to 10. And we're going to have to pick the best one for the design parameters of each problem that we're solving for. So I think that the answer to lots of large keys is unfortunately changing the way we're going to have to do upgrades to our protocols, and we're going to have to change the way we design our protocols so that we can accommodate the not generic platforms, but more specific solutions to specific problems so that we get the right performance characteristics. Because math is math, and unfortunately, to make some of these secure, you just do need to either have, it's a trade-off. You shift from, a small signature to a big key, and, you're trying to find the sweet spot for a specific problem. Okay. Thank you. Sir.
Yeah. I'm with the company Cryptomatic. We have been implementing software solutions using HSMs for almost 40 years, and we have been talking about crypto agility for, I would say, 15 to 16 years, and we have a true crypto agile platform for key management and key usage. One of the things I've learned by visiting financial institutions, semiconductors around the world is that it's either if they are about to fail an audit, or if there's something that is being deprecated, or the senior management tells them that the security team has to implement something, that they will do it, unless they will just wait until they actually have a security breach or something like that. In the European Union, NIST 2 will go into effect next month. It's not specific around post-quantum, but it tells that you need to do risk assessment, you need to start building an inventory of your cryptography estate. Do you see that at some point we might need something similar to make sure that the industries actually pick this up, and it's not just the vendors and the government that is pushing for it?
I think the government has done a lot for us recently. I'm not a big fan of regulation in general. But I do think that we've been given a lot of, as a security industry, a bunch of interesting opportunities. SEC requiring publishing security incidents, conversations in Europe around software liability, some conversations around software liability here in the US, some court cases showing that there are consequences for bad decisions. And my hope is that fear that people feel in the midst of a compromise might be felt a little bit earlier as a result of seeing your competitors, having their dirty laundry aired, and people be able to respond more proactively. So I never would have thought of me as an optimist, but I'm personally hopeful that we start to see people be more proactive on these topics. Any other thoughts on this one?
I think, as I was mentioning before, as people want to work with the government or work with other industries, I think, as you mentioned the risk assessment and all that, I think that the contracts part of it will be important as well. Like if you don't have certain things built into your products, you may not be able to do it. And if you haven't gone through validation or anything like that, working with NIST or anything along that sense, it might not be, you might see some hurt in the stock price. So,
one of the things related that sort of just popped to mind is the Intel Scepter vulnerability. I actually saw large manufacturers negotiating with vendors about the downtime felt for contract renewals and future prices. As soon as businesses start to feel in their commercials that their neglect is hurting them either on the sell side or the buy side, I think that'll also help fuel some of these changes.
Yeah. So actually regarding NIST 2, a company can get up to 2% fine of the turnover. So it's really significant, and even senior management could go to jail.
Yeah.
So it's really to push for this. So it's pretty tough.
Yeah. Thank you so much for the question.
Hello. On the topic of deprecating and sunsetting classical public key cryptography, I'm a big fan of stopping using cryptography as soon as possible if it's covered with a decent replacement. But it strikes me there is a difference in the threat model between key establishment and authentication when it comes to public key cryptography. There is no store now, man in the middle later attack. Is there a case for emphasizing more the key establishment deprecation rather than the signature deprecation? Or should we just try and give it all as soon as possible?
So if I understand you correctly, you are asking about that whether we can rely on the symmetric key cryptography. That's your question. Can you please
No, I'm saying that public key cryptography we use both for key establishment and also for authentication from signatures. Yeah. And the threat model for a failure of key establishment and a failure of signatures is different because there is no store now, man in the middle later attack. Mm-hmm. So we don't have that sort of future-proofing that we need to do for signatures. Therefore, is there a case for setting a different deadline for deprecating ECDSA than for deprecating ECDH?
That's a very interesting question. Thank you for bringing this one up. Yes, different. Well, for the secure definition, actually, it's kind of different because for the KEM, key encapsulation algorithm mechanism, we want it to be CCA to secure. That means indistinguishable to encryption ciphertext. And for the digital signature, that's for the not forgeable, right? So, however, I see your point, consider the usage, right? So the key establishment, you often want the long-term something, right? For example, you can interact, capture now and decrypt later. But for the digital signature, if it's only used for the entity authentication, if you cannot do anything, you cannot do anything. Past. Right. However, at this moment, I think we haven't considered to distinguish the different dates for the KEM, the classical KEM, like a DPM key agreement, and ECDH and ECDSA. We haven't, not yet. But you brought a very interesting point. I agree with you.
I think it makes sense for there to be prioritization of one over the other, certainly on the implementer side. My thought on this is that because we don't have inventories, since this isn't a conversation on inventories, it's really quite hard to be able to assess, whether or not, one, the shared threat models that might exist and what the intersection with the consequences might be. It's very difficult to say in a policy, I think, and thankfully I don't have to write any policy, but how to achieve that without accidentally leaving something out. I think for me it feels more like a recommendation space for where you should focus, and we'll be honest, to be honest, I suspect that we'll see classical crypto in use well beyond 2035. And so we just need to, give as practical, targeted advice as we can to help people minimize that. Did you have something you wanted to add?
Oh, no. I totally agree with you. I do feel like we will see some of that classical crypto as we migrate over, and just knowing that some agencies in the government space will not be able to flip over that quickly. So there will be some need for possibly some hybrid use. So yeah, I think it's still going to be around. It's just like, SHA-1.
So I'd like to make sure to thank our absolutely awesome panel. I don't think we could have done any better for our topic today. So I want to say thank you very much for making time. And I would say if there's anything to take away that on cryptographic inventory, my takeaway from this conversation is it's best to start now and get something minimal in place that you can get and have a plan on how you grow into having a more comprehensive view. Starting at the basics on software ingestion and maybe network analysis is going to be a great tool for people to be able to assess the risk of post-quantum threats as well as become more agile. And then the other thing I would add in is that it actually is a very useful tool to be able to point out in a concrete way where your weaknesses exist. So you might be able, as on the buy side of the industry, be able to justify to leadership where you should be making investments in a real tangible risk management proactive stance. So thank you very much. I appreciate everyone's time.
Hello, good afternoon. Special time of the conference, end of Friday. So we've got some great speakers here for you today in the post-quantum crypto track. My name is Jansen Liston, and I'm in charge of North America sales for PQ Shield. I'd like to get us started off with Daniel Chu, who's the chief cryptographer of Arkit. Thank you.
So, thank you very much for the introduction. Thank you very much to ICMC for letting me come back and speak again. And hey, well done you. It's been a long week, and you've almost made it to the end. Hoping to see lots of big smiles here. Wishing they hadn't given me the after lunch slot when everybody's just feeling a little bit full and sleepy. And this is the best time, obviously, to drag out the quantum cryptanalysis talk. So a little bit about me then. I began my life as an academic mathematician. My doctorate's in number theory. I spent a little bit of time as a high school teacher, but then I went for 20 years to work for the classified bit of the UK government. And it's only really for the past 3 or 4 years that I've been out in industry working in Arkit, where my job title is Chief Cryptographer, which makes it sound like there's lots of cryptographers hanging around. Not as many as there used to be. It's a small group, but very, very talented. And to be honest, when I sort of wake up and look in the mirror in the morning, I don't think of myself quite as much as a cryptographer as a cryptanalyst. They're two complementary skills as I go on, but it's cryptanalysis that I'd really like to talk about today. And looking at the slides, you'll see that they were prepared in a bit of a hurry, because I do know how to spell introduction, for which I apologize throughout. And I was asked over lunch, when you say a gentle introduction, that's a weird word to use with cryptanalysis. How gentle should it be? So I was challenged to sort of try and explain what I wanted to say in such a way that some of my old high school students could understand it. I've tried, but I'm going to have failed. Not to say they weren't a bunch of bright kids. But my hope is that you'll at least get something out of it. And next time these subjects come around, you'll learn a bit more and a bit more. Because the big why here is, I like to offer a different take than some of the other things, talks that go on here today. And we've had some absolutely fantastic talks this week about the fact we're about to bet the security of the internet on a whole bunch of new algorithms. And we've got lots and lots of people getting very, very excited and saying everybody should get excited about post-quantum cryptography, lattice-based cryptography. And well done, everybody involved. It was a long, messy process. Standards are out there, and it's a marvelous time to be here. But I also need people to get excited about lattice cryptanalysis, the idea that you should look at these things and think, how robust are they? How prone are they to breakage? Because you need these two skills to go hand in hand. You need people to build confidence in the algorithms, that you've looked at them hard, and where cracks do start appearing, such as we saw with SHA-1, we've got a couple of early warning signs, we need good advance warning so that we can start making some of the changes or some of the parameter variations that might be necessary. I've detected some caginess when people start talking about these algorithms, sort of saying, well, it's early days yet. People tending to sort of favor the larger parameter sets, where people are sort of phasing out 256-bit elliptic curves. They're saying, I want to use Kyber 768, I want to use dilithium 3, which is really one category up from the sort of existing level of these. So that sort of caution is very natural for cryptographers, but I'd like to sort of build a bit more confidence within the community to sort of say these things have been looked at hard. And also, there's a sort of lack of diversity that I think also is making people a little bit worried. So we need a little bit more confidence in these, or we need to sort of see what we need to think about for some of the replacement algorithms. So listening to my friend Margaret yesterday, who's a very smart woman who doesn't like saying she's a very smart woman, sort of saying lattices are ugly and nobody likes them, I'm hoping that we can change that, and as a group we can sort of all start understanding a bit more, start feeling a little bit better and nicer about them. But yeah, there's a lot of things I realized that I could be saying in this talk as I sort of sat down to plan it. There's lots of interesting things going on in lattice cryptanalysis, improvements to lattice basis reduction, improvements to lattice sieving. But the one I really want to talk about is the sort of quantum approach to cryptanalysis for lattice-based algorithms. This is, in some senses, the one that worries me most, because this is the big motivating case behind the new algorithms. And the sort of whole learning with errors approach was first sort of punted out as a sort of possible approach to lattice-based algorithms by a paper called Oded Regiev, and it came with a nice sort of bit sort of saying, and here's some questions you might like to consider about the lattice, quantum security of lattices if we're going to go in this direction. And it's remarks that very few people have picked up on. And in some sense, I'm trying to tidy up some of those arguments and trying to make them more accessible, more palatable to a general audience. But it's not surprising that few people have picked these up. Cryptanalysis is a hard skill, and very few people sort of would claim that they feel very strongly confident about it. And quantum algorithms is a very, very difficult skill, and very, very few people would say they have a good understanding, a good grasp of how quantum algorithms work. And if you look at the intersection of those two, you start looking at a very, very small community that everybody sort of looks at and sort of says, that person should be the person who knows it. And having grown up on the story of the Emperor's New Clothes, having taught the sort of story of Emperor's New Clothes to my daughter, always been very worried about taking other people's word for these sorts of things. So I do like to try and understand these things for myself. But then also, the teacher in me likes to sort of try and spread that as much as possible. You should be asking yourself, how well do I understand the reasons why we talk about lattices being quantum secure? What are the possible quantum lines of attack on these things? So don't feel you have to understand every slide, but the further into this talk you can get, the more you can start asking questions, the more friends you have that are cryptographers or that are quantum algorithm people, the more you can start asking the questions, the happier we can all get as a community. And that's the sort of goal. So that's to try and make it as accessible as possible. And again, I warn you, I'm going to fail badly. Okay, everybody feeling happy and comfortable? I'm not seeing any dissenting faces. Nobody's running for the exits. So what it comes down to is two pictures. So here you've got two shapes, but again, cryptanalytically speaking, I've had to try and fit anything on a slide. If these things actually had sort of 2 to the 1,000 odd edges or corners on them, that would be sort of the cryptanalytic point I'm trying to make. But on the left, you've got this sort of saw wheel thing, where with every sort of corner on the saw wheel, I've associated a number. But there's this interesting feature to the saw wheel that the numbers start repeating every so often. And if I just said to you, I'm going to give you a rule that sort of says, name any point on that wheel, I'll tell you the number in it, and your game is to find out what that sort of period of repetition is, that's something we call the hidden abelian subgroup problem, that sort of lovely cyclic structure. And if that's all I give you, we've got lots of theorems in mathematics that you can sort of start applying to this. I sort of say, if all I give you is the ability to evaluate that function, and a classical computer, you can't really do better than the square root of the number of points on that circle, really, or square root of the number of points in that subgroup. And all you can do is just sort of randomly start asking for points. But with a quantum computer, what you're allowed to do is sort of say, well, I want to understand what happens if I sort of treat this as a sort of generalized distribution. I can inquire about what's happening at the whole sort of things. If I was to sort of say, at some point later I'm going to pick a point, let's try and start doing computations, and then at a later point maybe I can start picking out the points of it. And if you do that, you only need to evaluate it once. This is the hidden abelian subgroup problem. Okay. That's the picture on the left. The picture on the right is something quite similar. Again, I've got a polygon with lots of sides, and in each corner there's a number attached. And again, I'm going to sort of say, I'm going to say to you, name any corner on that polygon, I'll tell you the number attached to it. But now, the sort of structure is that there is a line of symmetry about this polygon that it sort of reflects on. You've got the same numbers on either side of that reflection. So you've got this reflective pattern rather than this sort of rotational pattern. And the game is, you've got to try and find out what that line of symmetry is for me. And again, if all you had was a classical computer and all I let you do was name corners and I'd give you numbers, you couldn't do better really than the square root of the number of corners on that polygon. And again, can you do something cleverer with a quantum computer? Yes, you can talk about the distribution of the thing, say maybe I'll pick a corner later, start sampling those. Okay, now, take nothing else away from this talk, think about those two pictures. That picture on the left is what it takes to break factorization, elliptic curve discrete logarithms, multiplicative discrete logarithms. Everything we talk about with Shor's algorithm is covered by the picture on the left. Picture on the right is a quantum algorithm that is likely to give you a very, very big leg up at attacking lattice-based crypto systems. Now, you might say that these feel like very, very different questions. I'm not saying that's not going to be the case. Or you might sort of say to yourself, ooh, those questions sound worryingly similar to me. And it's that sort of level of worry and confidence building that I'd really like to sort of start moving you towards. Okay, so just, if nothing else, take away that picture, because now I'm going to start putting some math around it. Okay, so I've said that Shor's algorithm was basically the picture on the left, that sawtooth thing. Some of you may have seen this before. This is how you go about using a quantum computer to attack elliptic curves. So if you've got a point on your elliptic curve h, and you know that it's some scalar multiple of the point g, here's how you use a quantum computer to break it. You create a superposition of integers c and d. Okay, that's again just sort of saying, rather than just picking a corner of that saw wheel, I'm going to sort of say, can I just sort of think about all of the corners of the saw wheel at the same time, and I'll pick one of them later. That's all it's saying. So those numbers c and d just represent picking a corner of that saw wheel. Okay? Once you've done that, you haven't picked C and D necessarily yet, you're just in this superposition. Are we still doing quantum gags? On Tuesday we decided we needed more gags in the post-quantum talks. So this is a superposition to be in. You've got these C and this D, and that then allows you to compute a multiple of one of these points that you're interested in, H, and a multiple of another one, G, take the difference between those 2 points. And you can do this on a quantum computer without necessarily having decided what C and D are yet, just keeping it in that superposition. And these sort of little lines and angles that I've got next to it, that's just a way of saying, I've got this probability distribution in my quantum computer where I haven't really decided what things are because I haven't measured yet. Okay. Now, mathematically speaking, then, I'm going to drag out some group theory and sort of say, I can think of this as an element of a group, an abelian group, which corresponds to those saw wheel type things, where it is, if you know some mathematics, just the cyclic group of elements, L elements, crossed with the cyclic group of L elements, where L is the number of points on your elliptic curve. And then associating with that group element some function, just sort of saying, give me the number that's on the corner of that thing. So C and D, or gamma, you think of picking out a point on your saw wheel, F, or calculating that CG minus DH thing, working out the number that goes on that bit of the saw wheel. But as soon as you start thinking of that, you can use another clever bit of mathematics. Oh, well, you sort of say, this has actually got a nice bit of group theoretic structure. It says this function f, the one that's dotted around the saw wheel, has the property that if I take two things that are this fixed distance apart around the saw wheel, then the function's going to be equal on those. And that's the sort of magic thing that goes on there. And in particular then, that sort of fixed distance in this particular case corresponds to pairs where the sort of difference between 2 points is some multiple of A, and you don't necessarily know which one. Point is, you can then sort of throw something at that called Fourier analysis, which is very good at picking up periodic behavior. If you know about Fourier transforms from signal analysis, it's a related concept. Move from a time domain to a frequency domain, but you can back up that sort of Fourier transform, and because of the magic of quantum computers, you can do this again without having specified a single point, just having evaluated the whole sort of shape in one go. Then,
After you've done that inverse quantum Fourier transform, you've got a very spiky function. Now you can go back and sort of say, oh, I'm going to make my choices about my probability distribution now. And lo and behold, you'll get a pair of numbers that are A, T, and T. And then you just divide one by the other, you've recovered A. If you've seen that before, I hope you'll say that, yeah, that's pretty much Shor's algorithm on a slide. If you've not seen it before, imagine that I'm just going through the process of how a quantum computer thinks about that saw wheel. And this is Shor's algorithm. That's what we've all been terrified about. I can show you other variations of it that do factoring for RSA numbers, or I can show you how it works for multiplicative Diffie-Hellman. But this is well known, and this is the sort of big thing that we've been worried about since at least 2016, if not before 1990 whatever. Okay, so that's a mathematical description of how I'd go about with one of these big shot cryptanalytically relevant quantum computers that's going to appear any day now, of how I'd go about breaking NIST P256 or ED25519. What about learning with errors? What about Kyber? What about dilithium? So now, here I've got something like, or Frodo even, here I've got to think about finding vectors E and S such that this matrix equation, AS plus E equals B mod Q. If you know learning with errors, ring learning with errors, modular learning with errors, you know that it all comes down to some sort of problem that looks like that. And again, what I can do is I can sort of say, okay, pick any vector X, and I can look at what A times by that vector, my matrix A times by that vector looks like, and I'll get a lot of points dotted around in some sort of space. Again, I've got the frustrating problem that I want to be talking about lattices with hundreds and thousands of dimensions, and I've got a two-dimensional thing. So there you see a two-dimensional array of dots. Imagine that's 100 dimensions, and try not to get too much of a headache. And again, if I'm on a classical computer, yes, I can just sort of say, I'm going to pick an X, that gives me this point. I'm going to pick an X, that gives me that point. With a quantum computer, I can sort of say, tell me about that sort of whole sort of pattern, or maybe choose X later. Okay, I'm hoping and thinking, yeah, that would be easy to do on a classical computer. I'll assume that there's some magic that the quantum computers do. What else can I do? Well, I know A and I know B, so I can also calculate numbers AX plus B, where B is another vector. And again, different X, I'll give a different red dot if I was doing things classically. And classically, I just hope that sooner or later one of the black dots I'd done was really close to the red dots, and that'd be a really stupid way to go around solving lattice problems. On a quantum computer, I can calculate all the red dots and all the black dots together, and that's very important because the distance between the nearest red dot and the nearest black dot is just the same as that vector E that I'm looking for. And if I can get my hands on E, I can get my hands on S, everything falls apart horribly. Okay, but I'm not allowed to just sort of say, okay, quantum computer, you're thinking about all of those, give me the red and the black one that are closest together. Doesn't quite work that way, or at least I haven't thought of a way to make it work. What I can do though, and what Regiev sort of said, was you can then divide up your space where you created these red and black dots, and just sort of say, I'm going to create boxes where it's easy to calculate what box a black dot lies in, what box a red dot lies in. And what tends to happen, because the red dots and the black dots each have these nearest neighbor things, you tend to end up with boxes with one black dot and one red dot in, and the two that are in there are the same ones. That's not a universal truth. There are some times when the pairs get split up. There are some times you get more than one in there. As a general principle, you can then start to say, okay, I'm putting this grid on top of it. Mr. Point, which box do you lie in? Mr. Red Point, which box do you lie in? Mr. Black Point. Okay, I claim that's easy to sort of do classically, and then that's easy to do in superposition if you've got a quantum computer. And I hope I'm convincing you of this as well. Okay, so let's go back to the quantum sketch and ignore the top line where I failed to update the bit where I was talking about elliptic curves. Let's try and do some of this, the lattice problems that I have. So first of all, let's create a superposition of lots of different points in space, y and delta, where y is just either ax, the black points that I was creating, or ax plus b, according to whether delta is 0 or 1. So it's just giving me lots and lots of these points, and delta is just saying, are you a red point or a black point? Then complete that little square, that little block that your point lies in. Whether you're a red point or a black point, it's easy to compute the block that you lie in and sort of say, okay, so we've now got this lovely coordinate of your point, a label as to whether you're red or black, and then this block that you lie in. And the interesting thing here is, that's roughly going to have the property that if you treat y and delta as a special particular sort of group, it's just evaluating a function on that group, where the group in this particular point now is now CQ cross CQ cross CQ up to the dimension of the lattice, crossed by a semi-direct product of C2. Now, if it wasn't for that sort of... So you'll notice that I've used the funny multiplication sign on the end there. That's because it's not quite the sort of sawtooth thing. That sort of says, rather than a sawtooth, you've got a polygon. And if that little line wasn't there, I'd be breaking out Shor-Gauss' algorithm straight away, and we'd be sort of saying, looks like lattices aren't a worker. How much defense is that little short line providing you? How much is the difference between the sawtooth and the polygon buying you? Because what's the property that this superposition has? Well, again, we've got equality on those functions. We've got two things being in the same block if the difference between the points represents the short vector E and the difference between a red point and a black point. So that's, again, just a group theoretic construct. So can I then sort of use some equivalent of the Fourier analysis that I used on the cyclic group, that I used on the saw wheel, the dihedral one? So is there some nice analog to the inverse quantum Fourier transform I can use to measure and get E? So no longer sort of saying a transform that detects periodic structure, but a transform that detects reflective structure. And that's the question that I would sort of put to you all, that Reggiev put in his paper and not enough people have been looking at since. The question is there a Fourier transform for these semi-direct product groups, these dihedral groups, these reflective groups? And the answer is yes, if you've done a course in representation theory, which I'm afraid my undergraduate career was too early to sort of get some of these things. There is a whole Fourier theory around other groups, in particular these semi-product dihedral groups. And there is a dihedral Fourier transform. Frustratingly, I spent, I think it was 3 months reinventing it before defining the paper that it was done by Ettinger and Hoyer. But here's a quantum circuit that does evaluate a dihedral quantum Fourier transform, where this block here just sort of says, do that inverse quantum Fourier transform that Shor was talking about. And this bit here is just saying, do a uncontrolled single Hadamard gate. So really not that much more complicated than the classical Shor quantum Fourier transform. So it can be evaluated very quickly. What it's not clear to me yet, and wasn't clear to Reggiev, but I hope somebody who did do a course in representation theory and can save me having to read up on the whole literature of representation theory can tell me, is there a way of abstracting that reflective subgroup structure from the Fourier coefficients of the characters of the dihedral group? Okay, I probably started scaring people around about the word dihedral or semi-direct product, or possibly even around about the time of superposition. But it's an interesting time to be here. So we all got a very nice surprise earlier this year in April when somebody sort of said, oh, I've been thinking about quantum algorithms and lattice problems. And I went, oh, good, me too. It's very, very interesting, using all the right words that I was hoping to sort of see there, establishing a superposition of points of the lattice, although wanting to make it infinite rather than that sort of contained group of Q there, making it decay off at a nice Gaussian rate, though. And then looking within it, started sort of seeing, oh, yes, and he's talking about dihedral cosets in this. This is exactly the sorts of words I'm looking at. And before I got too deep into the paper, other people were already bouncing up there and sort of saying, there's slight issues with some of the things here. So there were issues with this paper, but it was asking the right kind of questions, and we need more people with eyes on this sort of thing that can pick up that sort of area. So yeah, I think very, very fertile ground for doing more of this and gaining more confidence in the quantum security of lattices. At the flip side of this, one could ask, well, how much confidence can we ever gain that something's going to be quantum secure? Are there any other sort of underlying results that sort of say some things are going to be hard? In the sort of classical world, we always used to rely on these black box theorems that sort of said, if you've got a generic group, you can't really do better than these square root algorithms. And yes, it is possible in the quantum world to start doing some of these underlying hard bounds. And in particular, we know, for example, that Grover's algorithm is optimal. You can't do better on unstructured search than that. So it is possible to also start proving results in the opposite direction. I've got 5 minutes, so that's hopefully the last sort of thing I need to say. Thank you all for sitting patiently towards the end of it. I hope you got something out of it. Don't worry if you didn't understand every single slide on it, but try to understand more. Try to search down people you might know to introduce in these questions, because I'd really like more people looking at the problem so that it's not just the emperor's new clothes where everybody's taking the words of two people for it. Thank you very much. Happy to take any questions.